The GPU prefix sum is a pretty handy algorithm that comes up every now and then, and I found it pretty interesting. I implemented it recently, so I thought I'd share how I did it. So I want to do an exclusive prefix sum. This means we have a list of numbers, and then we want to compute a new list where every value is the sum of all the preceding values in the original list. So here, the 11 is the sum of 3, 2, and 6. And the 12 is the sum of 3, 2, 6, and 1, and so on. Now, on a CPU, that's pretty straightforward to do. You just iterate over the list and keep track of a running sum, and you're done. But on a GPU, that's much harder to do. The GPU doesn't like doing one big batch of sequential works. It wants to do many small parallel parts. So how can we get it to do this? I went with something called the Blalock scan. It divides the task into two distinct phases, the upsweep and the downsweep, each of which consists of several passes. For the upsweep, the first pass computes the sum of every pair of number and it stores it in the rightmost value of that pair. The second pass then takes the output from the first one and computes the sum of the two numbers and stores it in the rightmost one. And the third one does the same, and so on and so on. In this case, we only needed 3 passes. And we ultimately end up with the total value and this list of intermediate sums. The next step is then to replace the last value of the list, which was the total, with 0, and then we begin the downsweep phase. For the first pass of the downsweep phase, you take the last number and the middle one, you store the sum of them on the right and the rightmost one on the left. So here we store 12 plus 0 to the right to be 12 and 0 on the left. And then in the next one, you work with the rightmost value in the center of the sublists. So, for example, you store 12 plus 8, which is 20 on the right, and then you store 12 on the left. And then for the third pass, you do the same thing for the now 4 sublists. So as you can see, each one of these passes consists of several jobs that can be done in parallel, and then you need a barrier between the passes for all the threads to synchronize. This is all well and good, but the problem is that you need the barriers. The barriers on the GPU really work within one workgroup, as far as I'm aware. So you're limited by the workgroup size of the GPU as to how big of a prefix sum you can calculate. But you can get around this limitation by stacking them recursively. So imagine we have this long list here, and our Blalock scan works on 4 values at a time. Well, we can compute 4 small prefix sums in parallel by launching 4 jobs on the GPU. But then in addition to writing out each individual prefix sum, we store the total of them in a separate buffer. So we have the total sum for each one of these blocks, as well as the prefix sum for each block. We can then do a second iteration where we compute the prefix sum of the totals, and then as a final step, we can add in the prefix sum of the total to the local prefix sum for each block. So we add in 0 to this first one, we add in 3 to the next one, and so on, and we end up with the global prefix sum. That way we can get around any workgroup size limitation, and we can compute the prefix sum for an arbitrarily large list. Before we get into the implementation, what is this even good for? Well, 2 examples. We can do a compaction of a list where we have some element that we want to keep here, the B element, and some other elements that we don't care about. And we can do this by writing a vector of 0s and 1s, representing whether we want to keep an element or not. Then we do a prefix sum of that vector, and then we store each element that we want to keep at the index indicated by the prefix sum, and it produces a compacted list. Another application is sorting. So say, for example, we have these pairs of numbers. And we've generated them sorted by their first member, but we actually want to sort them by their second member. The first step will be to compute the counts of the second values. So in this case, we have 2 2s, 1 3, and 2 4s. So our count vector is 0 0 2 1 2. Then we compute the prefix sum of that. And then we go over a list of pairs. We look up the prefix indicated by the second number. We read what's there and atomically increment it by 1, and then store at the position we originally read. And by repeating that for all the values, we get them sorted by the second coordinate. So in this case, when we store, for example, this 1 2 pair here, we look at the 2, we read the position in the prefix sum, we get a 0 back, and we store a 1. And then we store this at the 0th position in our final output. And then when we get to the last value that also has a 2, so the 5 2 value, we look again at the second position of our prefix sum, which is now a 1 since we updated it. We read that 1 and we store a 2, and we stick it into this first position as indicated. And so on. And if you do atomic updates, you can run this whole shuffling step in parallel. You don't get any guarantee of stability. For a single pass sort, that's not required. Now, if you do modify this shuffling to guarantee stability, then you can do the sorting in multiple passes and you end up with a GPU radix sort. But that stability guarantee is a little bit more intricate. Finally then, what about the implementation? Here's the whole compute shader. It works on a workgroup size of 256. And we take in 2 buffers, right? The original counters and then also a temporary workspace buffer that will hold the totals for the recursive uplink. We also need some information about the mode. Instead of writing several shaders, I just wrote one and branched on a uniform, as well as some info about where our data starts and how much we have. The mode 2 and 3 is really the add back modes, and they're very simple, so we're going to skip the discussion of those. And mode 0 and 1 are basically the same. They just read from either the counters buffer or the workspace buffer. The first step is to load in the data into local memory. We have this local hist that's going to keep the small batch of counters we want to work on. Compute shaders have access to this faster local memory, but it's quite limited in size. And by reading all of our data in one big chunk, in one big sequential chunk, it should invoke coalesced memory reads, which are more performant than just randomly reading from the big buffer. However, I don't really know how to check for whether the code ends up doing that in practice. Then we do the upsweep phase. Then there's the writing of the total to the workspace buffer, and we set the final value to 0. And then we do the downsweep phase, and then we write it back to the global buffer. To invoke the CPU side, we see the same 4 passes or 4 modes replicated. So there's the initial pass where we run the prefix sum on just the counts, and then if we ran more than one prefix sum, we keep doing recursive applications that are 256, the length of the previous one. Then we do the same applications backwards, adding back the total into the chunk prefix sum. And then we do the final add back of the total prefix sum into the count buffer. What about the performance? I used this implementation in a second project that I might talk about in the future, where it took about 500 microseconds to do a list of 2 million values. This is on an RX 6750 XT. This was fast enough for what I needed. I haven't done any benchmarking against other implementations, but I think it's possible to achieve like a 5 to 10x speedup. Other implementations seem to report their performance as throughput, so like how many values per second can you do. I'm not sure how to correctly compare like a measurement of a batch like this into a throughput number. I mean, you can compute the throughput here. You get about 4 billion values per second, which is about an order of magnitude away from, a state-of-the-art prefix sum. But I don't know if there's something more intricate you should be doing to get a good benchmark. It would seem more relevant to run the same size batches with different implementations to compare which one is faster or not. But I think it's possible to get a significant speed up from this. Still fast enough for what I needed for the moment and simple enough to implement.